So, okay, we have that numerical is not yet completed. So, just we have seen that I A 1 is equal to V F 0, the pre fault voltage, right, divided by your Z 1 plus Z 2 plus Z 3, and this is an equivalent circuit, right. So, I A 1 is equal to 0.909 angle 0 degree divided by J in bracket all the your positive, negative and 0 sequence impedances. Here it is reactances, because R is not there. So, the I A is equal to minus J 0.252 per unit, and I A 1 not shown here. I A 1 is equal to I A 2 is equal to I A 0, because it is a series circuit. So, I A 1 is equal to I A 2 is equal to I A 0, that is minus J 0.252 per unit. Therefore, fault current is equal to 3 I A 0. This we have seen before. So, is equal to, when we are deriving all sort of your what you call that circuit connection for line to ground, double line to line and double line to ground fault. So, fault current is equal to 3. If I recall this equation number perhaps 7, right, is equal to 3 into minus J 0.252, that is minus J 0.756 per unit. So, this is the fault current. Now, if you see this one, that component of I A 1 flowing towards G, that means your this is a your what you call a parallel circuit. This equivalent impedance is this one for positive sequence. This equivalent impedance, this side is this one, this is J 0.23 and this side is J 0.20 and J 0.491. So, this is equivalent to these two are parallel, right. So, equivalent we have taken this one out as pre fault voltage. So, parallel of these two things here it is given here. So, this J 0.345 and J 0.69. So, that is J 0.23 and this side is your J 0.20 0.491. So, we are writing the component of I 1 flowing towards G from the generator side. That means, this is your I mean that component of I A 1 that is flowing from this generator side towards this point G, right. It is a parallel circuit. So, current accordingly current will be divided. So, this one actually minus J 0.252 into 0.23 upon 0.921, that because this is your this side, this equivalent of these two motor reactances is 0.23, right. Therefore, this is coming actually minus J 0.063 per unit. Now, component of I A 1 flowing towards G from the motor side, that means from this these two motors are there. From motor side how much current is flowing to the G, that means, right. So, in that case it will be your minus J 0.252 into 0.691 upon 0.921 or minus J 0.189 pu. So, this is this. Now, similarly, the component of I A 2 from generator side is same, because this negative sequence it is same, only the voltage sources are not here, but it is the same, and but their your negative sequence reactances all are same. Therefore, the component of I A 2 from generator side is minus J 0.063 per unit and its component from the motor side is minus J 0.189, same as before, identical, right. But all of I A 0 flows towards G from motor 2 side, because motor 2 in this diagram, the motor 2 actually is your what you call that is grounded, and this is ungrounded, star connected and ungrounded, but right. Therefore, all of I A 0 will flows through towards G from motor 2 side. Therefore, no part of I A 0 flows towards G from the generator side, that is 0. That means, if you look at the diagram, then this is the 0 sequence network, right. Whatever things will come, it will be like this, and finally, it is J 3.260. But if you look at the generator side, this is isolated, there is an isolation. So, no 0 sequence current can flow from the generator side. That means, that no part of I A 0 flows towards G from the generator side, that is it is 0.0. So, in that case, now the fault current of the from the generator towards G. Now, we know I A 1, I A 2, I A 0. Therefore, fault current from the generator towards G we know I A, I B, I C equal to 1 1 1 beta square beta 1 beta square 1, this is I A 1 I A 2, and from the generator side no zero sequence current. So, it is 0, just I told you it is 0. So, if you simplify, then I A will become minus j 0.126 per unit, because if you multiply this is your this one, your what you call I A is equal to this one into this one into this one into 0. So, minus 0.126 per unit. Now, I B is equal to take this is beta square into this plus beta into this. So, it is minus j 0.063 in bracket beta square plus beta, but beta square plus beta plus 1 is equal to 0, we know that. So, beta square plus beta is equal to minus 1. So, it is I B is equal to j 0.063 per unit, and I C is equal to minus j 0, again same as before 0.063 in bracket beta plus beta square, which is minus 1. Therefore, I C is equal to j 0.063 per unit. This is the fault current from the generator side. Similarly, fault current from the motor side, I A, I B, I C same as before 1 1 1 beta square beta 1 and beta square 1. So, this is your I A 1 from motor side, then I A 2, right, and this is your that I A 0 minus j 0.252. So, in that case your if you simplify, I A will become minus j 0.63 per unit. Similarly, I B will be minus j 0.189. Look, I told you from the your what you call from the motor side that I A 0 is equal to minus j 0.252. Therefore, I A is equal to minus j 0.63 per unit. Similarly, I B is equal to minus j 0.189 in bracket beta square plus beta, that is equal to minus 1, right. So, it will your minus that is one thing, I B is equal to this one, then minus j 0.252, because multiplied by 1, right, by 1 into this one. So, if you simplify, it will become minus j 0.063 per unit. Similarly, I C is equal to minus j 0.189 in bracket beta plus beta square minus j 0.252 is equal to minus j 0.063 per unit. So, from this, so this is the answer. So, from this example, we have seen that how to connect positive, negative and zero sequence network, and to find out the fault current from the generator side as well as from the motor side. An exercise I am giving to you, you will take the same diagram, same parameters, I mean all the parameters will remain same as an example 4 of the previous topic. What you will do? You will take a fault at this point, say near E, you will take a fault near E, and this fault should not be there. At that time there will be no fault here, but you take a fault at here, and accordingly you draw the your that circuit connection and compute everything, all the fault currents I A 1, I A 2, I A 0, and the your current from the generator side, fault current from the generator side and fault current from the motor side. So, this is an exercise for you, that you will take a fault here, but at that time you should not consider this. Next is another example. Suppose you have two generators that operating in parallel, they are operating in parallel. So, it is 11 kV 12 MVA 3 phase star connected generators operate in parallel. So, the positive, negative and zero sequence reactances of each being J 0.09, J 0.05 and J 0.04 per unit respectively. A single line to ground fault occurs at the terminals of one of the generators. So, you have to find out first the fault current, second one current in grounding resistor, that means this one, and third voltage across grounding resistor. So, these two generators are in parallel and they are identical 11 kV and 12 MVA 3 phase star connected. A line to ground fault has occurred here, and therefore, and this is your grounding resistance is given R n is equal to 1 ohm. So, as they are in parallel, and we will go for that whenever we do such thing, we go for per phase analysis. So, x 1 will be equivalent to J 0.09 by 2, because both are having same positive sequence reactance. So, it is J 0.05. Similarly, for x 2 J 0.05 by 2, that is J 0.025 per unit. So, once I mean first you have to make all these things, then Z 0 it is given that your 0 sequence your impedance or reactance is J 0.04, that is given, but at the same time one grounding resistance is there, R n is equal to 1 ohm here, and this machine rating is 11 kV and 12 MVA. So, this 1 ohm we have to convert it to per unit values on its machine rating, that is machine base we will take. So, in that case Z this is given 0.0 given plus 3 R n, all these things we know. So, J 0.04. So, it is 3 into 1, that 3 R n means R n is equal to 1 ohm. So, it is 3 into 1 and it is kV and divided by base impedance. So, base impedance is that generator your voltage is 11 kV terminal voltage and base your generator rating is 12 MVA. So, this is your 11 kV base and MVA base is 12. So, your 3 into 1 divided by 11 square by 12. So, then when you convert it to per unit, and it will be Z 0 is equal to total 0.297 plus, I mean this one we are writing fast, this one we are writing fast, 0.297 plus J 0.04 per unit. Now, fault current, actually IF is equal to IA is equal to 3A1, that is we are writing from line to ground fault, from equation 7 we are writing, because fault impedance is 0, ZF is 0. So, it is a single line to ground fault occurs at the terminal of one of the generators, but your it is your solid fault, right, that is there is your there is no your ground impedance. So, ZF is equal to 0. So, in this case IF equal to IA is equal to 3 I1, this is coming from equation 7, when ZF is equal to 0. You go back to equation 7 and put ZF is equal to 0. Therefore, IF is equal to 3 into 1 angle 0, EA is 1 angle 0, divided by, you put all these value x 1, x 2 and z 0 here, you will get IF is equal to 9.472 angle minus 20.32 degree per unit. This is that fault current in per unit. Now, once you get this fault current, you have to find out the your its exact value. This is per unit, its value in kilo ampere. So, in this case this is this magnitude of the fault current. So, in this case 9.472 is your per unit, and this is 12 MVA, because generator rating is 12 MVA divided by root 3 into 11, that is 11 kV. So, ultimately the unit of this current actually given as kilo ampere. So, this is actually base current of the generator on its, I mean it is 12 MVA divided by root 3 your kV, that is 11. So, if you do so, it will be 5.96 kilo ampere. Similarly, the voltage across grounding resistor. So, that is R n into your fault current. So, R n is 1 ohm, it is 1 ohm, and this one converted to per unit 1 divided by 11 square by 12. This is the base impedance of this your generator. If you take 11 kV base voltage as 11 kV and base MVA 12, that is the generator rating. So, this is per unit value into you multiply 9.472, that is in per unit current, that will become 0.939 per unit. So, therefore, your is equal to 0.939 into your 11 by root 3 kV, because we there your we want that voltage across the grounding resistor. So, it will be phase voltage. So, 0.939 and 11 is 11 kV is line to line. So, 11 by root 3 kV, that is 5.96 kV, this is the answer. So, these problems are I mean I have taken from this classroom point of view, that quite not very lengthy problem, otherwise this unbalanced fault, some of the problems are too lengthy. So, within the time frame all these things cannot be I mean solved here, but most of the things are basically your everything depends based on your symmetrical component. So, similarly, for the same example you assume that R n is equal to 0. I mean example 2, you for the same example you assume that R n is equal to 0. So, find the fault current in each phase and voltage of the healthy phase of a double line to ground fault on terminals of the generator. So, you have assumed that there is a double line to ground fault now and R n is equal to 0. So, same example, but double line to ground fault. So, in this case this is from equation 36 for double line to ground fault, the expression of the positive sequence current I A 1 is equal to E A upon Z 1 plus Z 2 in bracket Z 0 plus 3 Z f divided by Z 2 plus Z 0 plus 3 Z f, but in this case Z f is equal to R n is equal to 0 is given. So, this is 0 and Z 1 is equal to x 1, that is J 0.045, Z 2 is equal to x 2, that is J 0.025. These are all parameters from the previous example, and Z 0 as R n is equal to 0. So, Z 0 is just J 0.04 per unit, this is 0.04 per unit, and Z f is equal to R n is equal to 0, this is given. So, if you substitute all these parameters here, you will get I A 1 is equal to minus J 16.56 per unit, this is the positive sequence current. Now, from equation 33, if you go back to the equation 33 for your double line to ground fault. So, not showing it here because these are understandable, that V A 1 is equal to V A 2, this is one. Another one is another equation, that 35, this is from equation 33, that go back to that double line to ground fault, and this one from equation 35 V A 0 is equal to V A 1 plus 3 Z f into I A 0, this is from equation 35. Now, here as fault impedance Z f is equal to 0, because Z f is equal to R n is equal to, if you put here, then actually it is V A 0 is equal to V A 1. That means, V A 1 is equal to V A 2 from equation V A 1 is equal to V A 2 from equation your 33, and from equation as fault impedance is 0, that is V A 0 is equal to V A 1. Therefore, V A 1 is equal to V A 2 is equal to V A, they are same. This suggests what? It suggests a parallel connection anyway. So, that means, if you look into that V A 1 is equal to V A 2 is equal to V A 0 1 angle 0 minus this one. That means, when you did the double line to ground fault, there was a 3 Z f impedance here, because of this equation V A 0 is equal to V A 1 plus 3 Z f I A 0. Now, Z f is not there, Z f is 0, that means here that this is a direct connection. So, that 3 Z f term is missing here, rest same as the double line to ground fault. I did not put any figure number here, but it is the same diagram for that positive negative at 0 sequence, how it will be connected. So, if you go through that, go back to that double line to ground fault, then you will see. So, in this case, just hold on. So, in this case, one can see that V A 1 is equal to this voltage is 1 angle 0, not shown here, only E A it is shown, E A is 1 angle 0 minus of J 16.56 into J 0.045, that is I A 1 into your Z 1, and you have got I A 1 is equal to minus J 16.56. So, that means, your V A 1 is equal to V A 0, V A 2 is equal to V A 0, all are same, that is coming 0.2548 your per unit. So, this is your voltage V A 1, V A 2, V A 0. Now, in this here, if you put your what you call that apply KVL, then your this it will be Z 2 into I A 2 plus Z 1, Z 2 and Z 0, not so shown here, but it is understandable, you know, this is your Z 1, this is this impedance Z 2 and this is Z 0. So, in this case it will be I A 2 into Z 2 plus V A 2 is equal to 0, that means, your I A 2 will be minus V A 2 upon Z 2. So, it is minus 0.2548 divided by J 0.025, that is actually J 10.192 per unit. Similarly, here also same way you can do it, I A 0 into Z 0 plus V A 0 is equal to 0. So, you will get I A 0 is equal to minus V A 0 upon Z 0, that is your minus 0.2548 by J 0.04, that is J 6.37 per unit. Now, this so this one, I mean another thing from there, right, just hold on, that if you look at this one, this current, all currents are meeting at this point, because your fault you have considered the line to line faults in phase B and C. So, I A is equal to 0, that means I A 1 plus I A 2 plus I A 0 is equal to 0. So, that is why all these things are meeting at this point. This is your I A 1, this is I A 2 and this is your I A 0. So, I A 1 plus I A 2 plus I A 0 is equal to 0. Same diagram, only ZF is not there, because ZF is equal to 0. So, once you have got I A 1, I A 2 and I A 0, right. So, that means I mean next one is that I B is equal to beta square I A 1 plus beta I A 2 plus I A 0. Now, beta square is actually e to the power j 240 degree. So, it is minus 0.5 minus j 0.866 into that I A 1 is minus j 16.56. Similarly, beta is equal to the power j 120 degree. So, minus 0.5 plus j 0.866 into j 10.192 and I A 0 is equal to j 6.37. Therefore, if you simplify, I B will be actually 25.05 angle 157.6 degree per unit. Similarly, I C is equal to beta I A 1 plus beta square I A 2 plus I A 0. So, same as before, beta value substitute, then you multiply by I A 1 plus beta square into your I A 2 plus I A 0 j 6.37. So, in that case I C also you will get 25.05 angle 22.4 degree. Now, from equation 31, V B is equal to V C is equal to 3 Z F I A 0. This we have seen for double line to ground fault. So, but Z F is equal to R N is equal to 0, that means V B is equal to V C is equal to 0. So, that means from equation 34, if you go back to equation 34, it is V A 0 is equal to 1/3 V A plus 2 V B. So, as V B is equal to 0, V B and V C both are 0. So, V A is equal to V A 0 is equal to 1/3 V A. That means, V A is equal to 3 V A 0, that is voltage of the healthy phase, because we have taken double line your double line to ground fault, that is phase B and C. So, V A should be 3 into 0.2548, that is V A is equal to 0.7644 per unit, because V A 1 is equal to V A 2 is equal to V A 0 is equal to 0.2548. So, this way you have to solve. So, no need to recall these formulas or put it in your memories, but you have to little bit practice. So, another one is, so this is that that although this kind of occurrence of this kind of fault is your very rare. So, what we will do it, that simultaneous two faults. One is that at phase A there is a line to ground fault, and at the same time phase B and C also there is a short circuit. So, that is another fault. So, simultaneous occurrence of this type of fault very rare, but we will see if it happens what will be the sequence network diagram, I mean how we will connect it. So, that is why a 3-phase synchronous generator with solidly grounded neutral is subject, I mean here no ground impedance, right. Solidly grounded neutral is to a line to line fault on phases B and C, I mean these phases B and C line to line fault, and accompanied by a line to ground fault on phase A. So, assume that synchronous generator was running on no load. So, you have to develop and draw the sequence network simulating the above fault condition. So, there is a line to ground fault on phase A. First, you have to put the boundary condition. If there is a line to ground fault here, that means V A is equal to 0. Similarly, further the phases B and C are also short circuited. That means, in that case V B is equal to V C and I B is equal to minus I C. So, that means V B is equal to V C because of line to line fault, and I B is equal to minus I C, because these two are together, it is there is a line to line fault. So, I B is equal to minus I C. So, and V A is equal to 0, these are the three conditions. So, from equation 1, I mean from this one you can write, just put it in positive, negative and 0 sequence. So, V B is equal to beta square V A 1 plus beta V A 2 plus V A 0 is equal to V C, that is beta V A 1 plus beta square V A 2 plus V A 0. That means, if you simplify, it will be beta square minus beta V A 1 is equal to beta square minus beta into V A 2. So, that means it will be V A 1 is equal to V A 2, because beta square minus beta, beta square minus beta will be cancelled. So, that means, and again from equation 3, again from this equation 3, V A is equal to 0, that means V A 1 plus V A 2 plus V A 0 is equal to 0. So, this is equation 4. So, from equation 4 and 5, so here it is V A 1 is equal to V A 2. So, if you substitute here that your V A 2 is equal to V A 1 in this equation, if you substitute V A 2 is equal to V A 1, then it will be your V A 1 plus V A 1 plus V A 0 is equal to 0, that means V A 1 will be equal to minus V A 0 upon 2. So, V A 1 is equal to, then V A 1 is equal to V A 2, therefore, V A 1 is equal to V A 2 is equal to minus V A 0 upon 2, this is equation 6. Now, again from equation 2, I mean from this equation, that I B is equal to minus I C, this equation also what we have to do is that I B is equal to beta square I A 1 plus this all we will know from symmetrical component. So, I B is equal to beta square I A 1 plus beta I A 2 plus I A 0 is equal to minus beta I A 1 plus beta square I A 2 plus I A 0. So, if you simplify, it will become beta square plus beta into I A 1 plus beta square plus beta into I A 2 is equal to minus 2 I A 0. That means, beta square plus beta is equal to minus 1, because we have seen the identity that beta square plus beta plus 1 is equal to 0. So, beta square plus beta is equal to minus 1, you put it here minus 1 minus 1, it is minus I A 1 minus I A 2 is equal to minus 2 I A 0. That means, I A 1 plus I A 2 is equal to 2 I A 0. So, this is equation 7. With this, that means V A 1, look, now we have drawn the sequence diagram for this one. So, V A 1 as V A 1 and V A 2, the positive and negative sequence networks are connected in parallel, because V A 1 is equal to V A 2. So, they will be connected in parallel. So, that is why this V A 1 and V A 2 they are connected actually in parallel. So, plus plus terminal connected, minus minus connected. Now, as I A 1 plus I A 2 is equal to 2 I A 0. So, this current is I A 1, this current is I A 2. So, leaving this terminal. So, 2 I A 0, and this current actually flowing to the 0 sequence network. That means, that the 0 sequence network is connected in series with the parallel combination of the positive and negative sequence network. That means, this is positive sequence, this is negative sequence, and this 2 I A 0, this 2 I A 0 current, because these two are in parallel, and this 0 sequence network is in series with the parallel combination of this. So, that means, from here as it is in series, so it will come to the from here it will come to the negative terminal here, and from here it will be and from positive terminal, from here it will be connected here, such that here also if you apply your KCL, I A 1 plus I A 2 is equal to 2 I A 0. Here also if you do so, that both the current I 1 I 2 leaving and this is entering. So, same philosophy, that I A 1 plus I 2 is equal to 2 I A 0. So, this is that your what you call that your sequence network connection for simultaneous occurrence of a line to ground fault, solid line to ground fault, and line to line fault. So, with this we will close that unbalanced fault analysis. Thank you.